Hello, this is the first of several lectures that describe the direct stiffness method of analyzing structures. This lecture addresses the truss element formulation in a global coordinate system. Next will be a lecture addressing the assembly of the stiffness matrix and solution of the system of equations that results. Then following that, we'll discuss the formulation of beam elements, the formulation of truss elements in local coordinates, including coordinate transformations, and then we'll introduce 2D frame elements before moving on to more advanced topics. Let's get started. The basic matrix approach can be explained using the single degree of freedom spring system shown in this slide. Here we have an elastic system where the displacement is proportional to the load that is applied. When a load P is applied to a spring with a known stiffness K, we can predict the displacement delta that results. If we apply twice the load, then we get twice the displacement, and so on. If we expand this single degree of freedom system to multiple degrees of freedom, then the equations can be written in matrix form where we have a matrix of stiffness coefficients, K, multiplied by a vector of displacements, delta, that is equal to a vector of externally applied loads, P. The only difference between the single degree of freedom system and the multiple degree of freedom system is that the single degree of freedom system can be explained using scalar variables, while the multiple degree of freedom system is characterized in matrix form. Note that the displacement and the external loads are shown here as vectors, or matrices with a single column, but they can also be matrices with multiple columns. This solution technique is often called the direct stiffness method, where we define the matrix K as the global stiffness matrix or the structure stiffness matrix. Delta is the vector or matrix of nodal displacements, and P is the vector or matrix of externally applied loads. The capital K, delta, and P indicate that these variables are defined in reference to the global coordinate system. Lowercase variables would indicate that they were defined in reference to the element local coordinate systems instead. The general nodal displacements, delta, are the unknowns. So after we determine the stiffness coefficients K and the externally applied loads P, we invert the stiffness matrix and multiply by the loads to find the displacements. The overall goal of the direct stiffness method is to develop a set of simultaneous equations that can be solved to find the displacements delta. In practice, commercial software wouldn't actually use matrix inversion, however. It would instead use a more computationally efficient method like Gauss-Jordan, Cholesky decomposition, or a wavefront solution technique. Generally speaking, once the stiffness matrix and the load matrices are determined, it's basically a linear algebra problem that needs to be solved. There is only one global or structure stiffness matrix for each model. That matrix is square, and there is one row and one column in the matrix for each degree of freedom in the structure. For a plane truss, there are 2 degrees of freedom for each joint or each node. For a space truss, there's 3 degrees of freedom for each joint or each node. For a plane beam or a 2-dimensional beam, there's 2 degrees of freedom for each node. For a plane frame, there's 3 degrees of freedom for each node. And for a space frame, there's 6 degrees of freedom for each node. The displacements delta and loads P can either be vectors or matrices and have one row for each structure degree of freedom and one column for each load case to be considered. Let's take a look at the truss shown here. It's a 5-node truss with 7 members. So with 5 nodes, there's 10 degrees of freedom, and the stiffness matrix K will be a 10 by 10 matrix. If we identify the degrees of freedom like you did in the first homework assignment, then we can label those degrees of freedom as is shown here, where the horizontal displacement at each node is numbered 2 times I minus 1, and the vertical displacement at each node is numbered 2 times I, where I is the node number. For example, the first degree of freedom would be delta x at node 1, and the 8th degree of freedom would be delta y at node 8. Each element within the stiffness matrix is called a stiffness coefficient, and we're going to define a stiffness coefficient, Ij, as the force at the location and in the direction of the degree of freedom I that is required to cause a unit displacement at degree of freedom j, while all other displacements are held to 0. Basically, we're going to impose a unit displacement at one of the degrees of freedom, in this case the first degree of freedom, while holding all other degrees of freedom to a zero displacement. In order to do this, forces are required at many of the nodes. For example, we need a force at degree of freedom 1 to push the node to the right, and after we do that, we need a force corresponding to degree of freedom 2 to hold that node from translating downwards. Correspondingly, we need forces at degrees of freedom 3 and 4 to keep node 2 from moving, and we need a force corresponding to degree of freedom 5 to keep node 3 from moving to the right. There are theoretically forces corresponding to the other degrees of freedom, but they would be zero in this case. If we now impose a unit displacement to degree of freedom number 4 while holding all other degrees of freedom to zero, then we need a force corresponding to degree of freedom number 4 to move node 2 upwards by 1 unit. We, in theory, would also need a force corresponding to degree of freedom number 3 to keep node 2 from moving to the left or to the right. We would need forces at node 1 to keep that node from moving. We would need forces at node 3 to keep that node from moving, and we would need forces at node 4 to keep that node from moving as well. Next, if we impose a unit displacement corresponding to degree of freedom number 6, we would need force F66 to move that node upwards by 1 unit. In theory, we would need a force F sub 56 in order to keep that node from moving left or right. We would need forces at nodes 2 and 4 to keep them from moving upwards and to keep them from moving sideways. We would need forces at node 1 and node 5 to keep those nodes in place as well. Finally, if we impose a unit displacement to degree of freedom number 9 while holding all other degrees of freedom equal to 0, then of course we need a force F99 to move node 5 1 unit to the right. We would need a force F sub 10(9) to keep that node from moving vertically, and we would need forces at node 4 and node 3 to keep those two nodes from moving as well. Each time we impose one of these unit displacements, we create a column within our global stiffness matrix. So when we impose a unit displacement corresponding to degree of freedom number 1, we define the stiffness coefficients that are in the first column of our global stiffness matrix. When we impose a unit displacement corresponding to degree of freedom number 4, then we create the stiffness coefficients that are in the fourth column of the global stiffness matrix. And we get the sixth column for degree of freedom number 6 set equal to 1, and we get the ninth column for degree of freedom number 9 set equal to 1. By definition, the global stiffness matrix or the structure stiffness matrix will always be square, will always be symmetric, and should never have a zero or a negative coefficient on the diagonal. Before we can go any further, however, we need to discuss how the stiffness coefficients for each member are determined. There's one element stiffness matrix, K sub I, for each element or member within the structure. Each one of these element stiffness matrices has one row and one column for each member degree of freedom. If we're talking about a plain truss member, there's 2 degrees of freedom at each end, so there's a total of 4 degrees of freedom, or 4 rows and 4 columns in each member stiffness matrix. For a space truss, there's 3 degrees of freedom at each end, or 6 total degrees of freedom, so the element stiffness matrix would be 6 by 6, etc., etc. K sub I, where the K is capitalized, is the element stiffness matrix with respect to the global coordinate system. In another lecture, we'll learn about a K sub I where the K is lowercase, and in that case, it would be an element stiffness matrix in terms of a local coordinate system. The vector delta is a vector of element displacements in global coordinates, and it's made up of the end degrees of freedom. So you have delta x at the ith node, delta y at the ith node, delta x at the jth node, and delta y at the jth node. This is a capital delta, so it's written in terms of the global coordinates. In another lecture, we'll deal with a lowercase delta where we have displacements in local coordinates. We've already defined K sub I and delta sub I, the element stiffness matrix for the ith element and the displacement vector corresponding to the ith element. F sub I is a vector of member end actions or member forces that correspond to the ith element in the global coordinate system. Previously, we had written that for the structure, K, the global stiffness matrix, times delta is equal to P, the externally applied loads. For each of the elements within the structure, we can also write that K sub I times delta sub I is equal to F sub I. For a truss element, K sub I, the element stiffness matrix, is given as is shown here, AE over L, the generic stiffness for a member loaded axially, times a matrix of cosines and sines. The vectors delta sub I and F sub I are shown here. The values of C and S in the element stiffness matrix for a truss are the directional cosines for the member, cosine of phi and sine of phi, and those are determined as is shown here as a function of the element's orientation within the global coordinate system. We can determine the cosine of phi and the sine of phi when we know the coordinates of the nodes corresponding to the beginning and the end of the member, and we know the length of the element. Okay, so we've defined the stiffness coefficient K sub ij as the force required at degree of freedom I to cause a unit displacement at degree of freedom j while all other displacements are held at 0. Stiffness matrices are always symmetric, and we're given that for a 2D truss element that the element stiffness matrix K in global coordinates is given as is shown. Knowing that a stiffness coefficient K sub ij is the force required at degree of freedom I to cause a unit displacement at degree of freedom j, we can impose a unit degree of freedom corresponding to the first degree of freedom for this member. In other words, we move node 1 or node I to the right by 1 unit, as is shown here. By solving for the forces that are required to hold that element in that displaced position, we essentially solve for the first column of stiffness coefficients in the element stiffness matrix. Note that there is an axial deformation, lowercase delta, that corresponds to the shortening or elongation of the member. In this case, it's a shortening of the member. Also note that the equilibrium is based on the undeformed geometry of the member, not the deformed geometry. As a second step, we impose a unit displacement corresponding to the second degree of freedom for the element. In this case, we move node 1 upwards by 1 unit, and in this case, we calculate the second column within our stiffness matrix. As the third step, we impose a unit displacement corresponding to the third degree of freedom for our element, and that is to impose a unit degree of freedom horizontally at node 2. And in so doing, we create the third column in our element stiffness matrix. Finally, we impose a unit displacement corresponding to the fourth degree of freedom for our element. That is, impose a unit vertical displacement at node 2, delta sub y2, as is shown here. And when we solve for the forces that are required to hold the element in this displaced condition, or this deformed condition, then we essentially solve for the stiffness coefficients that represent the fourth column of our element stiffness matrix. So for our example truss with 7 members, there are 7 element stiffness matrices. Given that each member is made out of steel with E equal to 29,000 KSI and that each member has an area of 8 inches squared, we can determine the stiffness coefficients in each of the 7 element stiffness matrices. The stiffness matrices for members A, B, C, and D are shown here on this slide. And the stiffness matrices for elements E, F, and G are shown on this slide. This might be jumping ahead a little bit, but after we've solved the problem and we have the displacements that correspond to the degrees of freedom in our structure, we can go back and use a process called back substitution to solve for the member forces or the member end actions for each of the elements in the structure. We can determine the vector F sub I is equal to the element stiffness matrix K sub I times the vector delta sub I, the vector of displacements corresponding to the degrees of freedom for each of the elements in the structure. So, for example, if we consider member A, we can take the element stiffness matrix K sub A multiplied by our vector of known displacements that correspond to the member degree of freedoms, and we get the member end actions. In this case, 8.25 kips acting horizontally at each node and 11 kips acting vertically at each node. We can do the same thing for member B, and so on and so forth. To summarize the matrix analysis process as we know it so far, the first step is to identify and label the degrees of freedom at each node within our structure. The second step is to formulate the member or element stiffness matrices K sub I. Then we go through a number of steps in the process that we haven't yet discussed. Ultimately, we end up with the displacements delta at the degrees of freedom. Once we know those displacements, then we can back substitute or back multiply to get the member end actions or member forces F sub I. And then finally we can solve for the internal member actions. In the case of a two-dimensional truss element, that's the member axial force P.